यस, आई एम ऑडिबल।
यस सर।
यस, जिस ग्राफ की हम बात कर रहे थे, पीवी वर्सेस
हाँ
ग्राफ,
हाँ।
अगर वॉल्यूम वाला है तो वॉल्यूम में अगर डिक्रीज होगा तो टेम्परेचर जो इंक्रीज होता है, तो वॉल्यूम डिक्रीज होता है, तो वही रिलेशन प्रेशर के रिगार्डिंग होता है, डिफरेंट होता है।
और सर वो तो एक्चुअली जो बॉयल्स लॉ है वो तो एक्चुअली
हाँ।
P वेरिजेस 1/v होता है। तो P वेरिजेस 1/v को अगर हम लोग वो प्रोपोर्शनलिटी साइन एलिमिनेट करते हैं तो एक कांस्टेंट लाना पड़ता है। तो इसके बाद जो इक्वेशन बनता है वो PV इक्वल्स टू K यानी कांस्टेंट आता है। ये इन दिस केस Boyle's law is applicable when temperature is constant and the number of moles is also constant. So in this case, when PV versus V graph we are plotting, then PV equals to constant. So either we are increasing the volume or not, the product of P into V will be always constant in this case at constant temperature. But when
पीवी में
the
कांस्टेंट,
temperature
बॉयल्स लॉ में कांस्टेंट टेम्परेचर होता है, यहाँ पे टेम्परेचर इंक्रीज हो रहा है।
हाँ जब टेम्परेचर इंक्रीज होगा तब वो वैल्यू ऐसे इंक्रीज करेगा। पीवी का वैल्यू जब टेम्परेचर इंक्रीज करेगा।
तो ग्राफ कौन सा आएगा?
ये कांस्टेंट टेम्परेचर पे और ये जो टेम्परेचर इंक्रीज कर रहा है
हाँ,
तब
तो जो
उसको
क्वेश्चन
उस
हमारा
टाइम
है वो सेकंड वाला ग्राफ आएगा ना।
जो कांस्टेंट टेम्परेचर नहीं रहेगा तब सेकंड वाला ग्राफ आएगा।
हाँ, टेम्परेचर इंक्रीज होगा तब सेकंड वाला आएगा ना।
हाँ हाँ हाँ।
यस। यस, सही है, ये है।
और वो जो पी वर्सेस वी ग्राफ था, पी वर्सेस वी ग्राफ तो ऐसे रेक्टेंगुलर हाइपरबोला होगा और पी वर्सेस 1/v का जो ग्राफ होगा वो स्ट्रेट लाइन से जाएगा। वो आपने जो सेकंड फोटो भेजा उसमें से तीन मैचिंग थे। तो एक पी वर्सेस वी था, एक पी वर्सेस वी, एक पी वर्सेस 1/v। तो वो ग्राफ्स भी कर दिया।
यस, लास्ट डे हमने क्या किया था?
लास्ट डे हमने कोऑर्डिनेशन के थोड़े बहुत पार्ट्स हुए थे कंप्लीट। अभी वो बैलेंस बॉन्ड थ्योरी
हाँ,
आएगा और
मैं कह रहा था, हाँ बताइए। तो टेम्परेचर
सामने
जो
एक
इंक्रीज होगा वो सेकंड वाला आएगा, जो मैं अभी आपको बना के भेजा है, ठीक है। हाँ।
और वैसे वो आइसोमेरिज्म का पार्ट भी है। आइसोमेरिज्म, वीवीटी, सीएफटी, ये सब पार्ट अभी बाकी है।
यस, कैरी ऑन। लास्ट डे हमने डिस्कस कहाँ तक किया था? लिगेंड्स हो गए थे हमारे कंप्लीट।
हाँ लिगेंड्स हो गए थे।
लिगेंड्स तक ही हुआ था ना?
हाँ लिगेंड्स हो गए थे, उसके बाद भी थोड़ा बहुत टॉपिक हो गए थे।
थोड़ा बहुत क्या आइसोमेरिज किया था हमने?
आइसोमेरिज्म नहीं हुआ था।
तो वही हुआ था, लिगेंड्स तक ही हुआ है। अब नेक्स्ट टॉपिक हम मूव करते हैं, आइसोमेरिज। व्हाट इज आइसोमेरिज एंड व्हाट द डिफरेंस बिटवीन ऑर्गेनिक आइसोमेरिज एंड इनऑर्गेनिक आइसोमेरिज? एक्सप्लेन वन बाय वन।
Okay, sir. So isomerism means if the empirical formula will be the same and the mass of the compound will be also same, but the connectivity throughout the molecule will be different in each case. So in isomerism, we see many structure with similar formula, similar empirical formula, and the structure in between the structure, the connectivity towards a ligand or metal is different. So now in this case, we are talking about coordination isomerism. So coordination isomerism is basically inorganic isomerism. So in this case, this isomerism can be classified to two types. One is structural isomerism and another is stereoisomerism. So in structural isomerism, atom-atom connectivity, atom-to-atom connectivity is different. But in case of stereoisomerism, atom-to-atom connectivity is same. Is same, but the spatial arrangement is different. So in this case, when structural isomerism is covered, then we can see many types of isomerism that can be shown in coordination complex, like linkage isomerism, like hydrate isomerism, and also ionization isomerism. And there is another type which is coordination isomerism. So these are the types we can see in the structural isomerism part. But in case of stereoisomerism, we can see two types of isomerism are present. One is geometrical isomerism and one is optical isomerism. So in linkage isomerism, the ligand with the ligand connected with the center metal atom is changed. Like this is the example for ligand linkage isomerism will be this is the linkage isomerism.
यस।
And in case of hybrid isomerism, we can see the number of change in aqua molecule or H2O molecule. This type of isomerism is called as hydrate isomerism, or in case of ionization isomerism, an ion which is in the which present firstly in the previously in the spectator ion, and the ion which is in the coordination sphere ion will be alternated at a coordination complex. Then those two complex will be called as ionization isomer complex. And in coordination isomerism, there is two types of complex with same ligand. One is this, and another will be this. So this is all about the isomerism part of a coordination complex. And in case of geometrical isomerism, there is cis trans isomer present, and in optical isomerism, their enantiomer is present. This is all about coordination isomerism.
Yes, good. Yes, what the difference between organic and inorganic isomerism?
Sir, in case of inorganic isomerism, there is a structural isomerism part and a stereoisomerism part. But in case of organic isomerism, there is only stereoisomerism played the main role, where we can check the geometrical optical isomerism. This part is based on the organic isomerism, but in case of structural isomerism, this can be shown in an inorganic isomerism. Which is the linkage, hydrate, ionization, coordination isomerism. These are the inorganic isomerism part. But in case of stereoisomerism or organic isomerism, then we will see the connectivity with spatial arrangement is different.
Yes, what's the difference geometrical and optical isomerism?
So in case of geometrical isomerism, we have to draw some structures to understand the difference between so in case of geometrical isomerism, we can see so this is we have drawn two structure of a compound coordination compound. So in this case, where we can see the Cl ligand is attached with the central metal atom in a transposition. That means Cl, Co and Cl occupies the angle 180 degree. But in case of this, the Cl ligand are sitting behind, sitting each other closely. This means this shows this compound is cis compound and this compound is trans compound. So when a coordination complex or compound shows this type of spatial arrangement, when it shows a trans shape and a form of cis shape, then it will be called as each other's geometrical isomer, because there is a geometry, there is a difference in geometry. So these are geometrical isomer with same formula. But in case of optical isomer, we check if the compound which we are using has no plane of symmetry, and also the mirror image of the compound is not superimposable. Which is COEN whole 3 plus. So this compound, we check the mirror image of this compound, and which is not same when we draw the mirror image of this compound, and this is not superimposable to each other. So these two compounds are called as enantiomer, because this is the mirror image of this compound, and the enantiomer are not superimposable to each other. This is why it is called as optical isomer. So this is the main difference between geometrical and optical isomer.
Yes. What is linkage isomerage? What the example of linkage?
Okay. So in case of linkage isomerism, we check the donor atom from the ligand. So if we use a compound where CrNH3 whole 5 NCS is present and a compound where CrNH3 whole 5 SCN is present. In this case, this SCN and NCS group in first compound, N is the connecting ligand of NCS. N is the donor atom. And in this case, sulfur is the linkage or donor atom. So basically, this is an example for ambidentate nucleophile, ambidentate ligand, which is used in this case, where in first compound N is making the linkage with central metal atom, and in case of second compound, sulfur is making the linkage with chromium atom, central metal atom. So this is the example of linkage isomerism. The difference of linkage creates an isomerism regarding the formula of the compound is same.
Yes. What is the difference between optically active and optically inactive compound?
In case of optically active compound, we see the mirror image and the plane of symmetry. So if a compound is optically active, this compound must have two criteria. One, the mirror image of this compound is non-superimposable to each other, and also the compound we are considering has no plane of symmetry. If plane of symmetry is present and the mirror image of the compound is superimposable, then the compound is organic. Then the compound is optically inactive. But in case of the compound fulfilling both the criteria of not having any plane of symmetry and having a mirror image which is non-superimposable, then the compound is called as optically active compound.
Yes. Which spectroscopy identifies cis trans isomer?
Spectroscopically, maybe it is determined a compound which is trans and which compound is cis. There will be some variation in their peaks so that we can match the peaks with our data and check if the compound is trans or if the compound is cis.
Yes, EDTA. Explain EDTA. Chelate complex and non-chelate complex. Explain.
Sir, in case of chelate complex, we use any ligand which is multidentate or not monodentate. So in case of bidentate, tridentate, tetra or polydentate ligand, this type of ligand forms chelation with metal. So example, we are taking EDTA. EDTA is a large molecule with having 6 donor atoms. So when it so this is a complex with the ligand EDTA. Hexadentate ligand.
Yes. For the example of facial meridonium in isomer.
Facial meridional.
Yes.
So this is the structure of tertial and meridional isomer in case of Ma3B3 coordination complex.
Yes. Isomerism, any drawback and limitation of isomerism?
Sir, in case of isomerism, if the compound is optically active, then it can be used for many production, or in the case of production of optically active compounds. But in case of multiple isomer in a production of a coordination complex, then the purification or the distinguishment of the compound will be much tough, and the preparation of a particular desired compound is kind of strenuous process. So this is why in isomers, the mixture of isomers are quite uh, tough to separate. This will be the limitations for the isomers of coordination complex.
Yes, good. Next, move on. Next new topic, IUPAC nomenclature. What the main application of IUPAC nomenclature?
Sir, so in IUPAC nomenclature, we can do uh, the fundamental nature, or the fundamental groups present in a coordination complex is known by the IUPAC nomenclature. And through IUPAC nomenclature, we can predict the structure of a compound, and from the structure of the compound, we can predict how many ligands are attached to the compound, and also the oxidation state of the central metal atoms can be also known from the IUPAC nomenclature.
Yes. What is neutral ligand?
So the ligand which can share its electron to the central metal atom and make a coordination complex, but itself a neutral species, is called neutral ligand. The example for a neutral ligand will be NH3 and also H2O. These are the ligands which are neutral species, and this type of ligands are called as neutral ligand. सर खत्म कर दीजिए कोऑर्डिनेशन को.
खत्म तो नहीं होगा. कब जाएंगे आप?
मेरा तो 13th को है, मैं जाऊंगा 12 तारीख को.
12 को जाएंगे ना, तो अभी कोई दिक्कत नहीं. अभी खत्म, कोऑर्डिनेशन बड़ा है ना. मेन एप्लीकेशन यूजेस क्या है IUPAC?
Sir, the uses of IUPAC nomenclature will be, this is very helpful to identify a compound, coordination compound, and nomenclature shows us how many ligands and which type of ligands are present in a coordination complex. And also in IUPAC nomenclature, we can predict the oxidation state of a coordination complex. And also a complex is cationic complex or anionic complex can be also known from the IUPAC nomenclature. सर मैं चाहता हूँ मैं फुल 2-3 इंटरव्यू आपसे
यस
लेके
यस,
जाऊँ।
फुल दे देंगे, अभी टाइम है, कोई दिक्कत नहीं है, अभी टाइम है। थ्योरीज आप बता दीजिए, व्हाट द डिफरेंस बिटवीन बीबीटी, सीएफटी, एलएफटी एंड एसीएफटी, एक्सप्लेन कीजिए।
Okay, sir. So in case of VVT, this theory is based on magnetic portion, and in VBT we talk about how metal and ligand are connected, where ligand, the field orbital of ligand shares its electrons to the vacant orbital of metal and creates a coordination bond, and then we can know the structure of ligand and the nature of ligand. Structure and nature of ligand. So in this case, in DBT, we can get the shape of a molecule, of a coordination molecule, which is present and acts according to the complex. And but in case of CFT, it is based on how the ligand is approaches towards the complex, like in octahedral complex and in tetrahedral complex. From DBT, we can get the hybridization value and the shape of the molecule and which type of orbital is used. But in case of CFT, we can predict how a molecule is formed, coordination complex is formed, and why the ligand acts as strong ligand and weak field ligand. In case of BBT cannot display the reason of strong field ligand and weak field ligand. It partially guess the some ligands as CN as strong field ligand and Cl minus as weak field ligand. But the explanation of the strong field ligand and weak field ligand can be known from the CFT. And in case of CFT, it also explain the magnetic behavior of coordination complex, but BVT cannot explain the magnetic behavior and the magnetic value which can be predicted through the CFT. And also the LMCT and MLCT, these are the process of charge transfer. These are the charge transfer process. So when in LMCT, we can see ligand to metal charge transfer takes place, but in case of MLCT, metal to ligand charge transfer takes place. So the example of LMCT will be MnO4 minus, which is KMnO4. We can see that KMnO4 is highly colored, but it doesn't have any electron in its d orbital. But we have seen that when the d orbital is partially filled by electron, then it can show color. But in MnO4 minus, Mn has +7 oxidation state and D has 0 electron, but still it shows color. So this can be explained from the ligand metal charge transfer theory. And in MLCT, there is the theory which shows us that the field orbital of metal will share its electron to ligand and charge transfer occurs and color arises. So these are the main motto or the brief explanation of this type of theories which are highly important in our coordination complex chapter. और वो जो ये in CFT there is a term called CFAC, which is very important in our coordination complex chapter, because the CFEC determines the stability of a molecule and also the reactivity of a molecule. So CFEC means crystal field stabilization energy, that can be shown by the splitting of the d orbital after the ligand has approached to the metal. How CFSE creates and gives us the color theory, and also the stability of a compound which has the compound which has more CFSE will be more stable than the compound with having less CFSE. So these are the topics we can use in our coordination complex chapter to study any coordination complex. Okay, sir.
Yes. Any limitation of BBT?
Sir, the VBT limitation is it cannot predict the magnetic behavior of the molecule, because mu equals to root over n into n plus 2. This equation cannot explained fulfill way by the VBT, and also in VBT there is no explanation of the spectrochemical series like the strong field ligand or the weak field ligand. These are the topic which cannot be explained by the VBT, and these will be the limitations for valence bond theory.
Yes, CFT.
So by CFT we can predict the structure, and also we can guess, we can see the theory behind how a strong field ligand or weak field ligand, how a strong field ligand or weak field ligand affects the coordination complex, and how the color arises in case of a strong field, in case of a coordination complex. And also by CFT we can get the we can get the concept of CFSE, which is crystal field stabilization energy, which predicts us a value of a coordination complex, and also it can explain us the stability and reactivity of a coordination complex. These are the benefits of CFT in the chapter.